Alright, hi everybody. So in this video, I wanted to go over something called telescoping series. And you might notice this little number 2 over here because this is part 2 of the telescoping series. The telescoping series because there was a first video before this. So if you haven't checked that out or you don't know what a telescoping series is, I would highly recommend checking this video out first before watching this one, because you'll need to know the basics before you can handle this video. Because in this video, I'm not going to be going over what a telescoping series is. I already covered that in my other video. In this video, instead, what we're going to be doing is we're going to be seeing some more complicated problems involving telescoping series. And there's going to be a few more tricks and a bit more complicated techniques that we're going to have to use. So if you don't have a good grasp of the basics, you can't do this. Okay, so that's the first thing I'd recommend checking out, the telescoping series part 1. Okay, and also another prerequisite before watching this video would be some, being familiar with sigma notation. So that's this scary looking symbol over here. So if you're not too familiar with sigma notation, I would not watch this video just yet. I would first get real comfortable with sigma notation before watching this. And don't worry, I'll be linking this video, telescoping series part 1. That's on my other channel, 20 circles. And in the future, I should make something on sigma notation as well. So don't worry about that. In the meantime, let's get on to some more complicated telescoping series problems. So, as always, we have a method that we want to follow in order to evaluate these types of problems. So, basically, our goal is to manipulate the problem because we like manipulating in math. We like making things easier for us, and to get it into a form that we are very familiar with. So basically, it says over here that we want to manipulate this problem until it is in a specific form. And that form would be something like this. So we're going to be summing up, okay? Everything from k equals 2. So that's 2, 3, 4, 5, 6, all the way to our desired n. And this is our expression. This is the expression that we want to get it into, f of k minus f of k minus 1, where we take each value of k and increase it by 1, keep plugging it in here, and you're going to get something like this. So if we start with 2, we're going to get f of 2 minus f of 1. We bump that k up to 3, we get f of 3 minus f of 2, and so on and so forth. And you can see the idea here is that this f of 2 will cancel with this minus f of 2. This f of 3 will cancel with this minus f of 3, so on and so forth. And basically everything in the middle will cancel until we get just the last term, f of n, and the first term, minus f of 1. So basically this is just a more mathematical way of saying that we need to cancel everything in the middle, which we already saw in telescoping part 1. So it's the same thing, just written a bit more fancy, I guess. But with that out of the way, before we get into the complicated problems, I need to make sure that you know how to attack a problem that requires us to telescope. So I have a little warm-up example for you here. Feel free to pause and try it on your own before we get into it. So let's get into the good stuff. So for a problem like this, I hope you instantly thought to rationalize. So I'm just going to take this and get to work. So to rationalize this, we're going to have to multiply. So this first term, we're going to multiply by the conjugate, which would be the term in the bottom, just with the sign flipped. So if I go ahead and do that very quick, what we're going to get is this first term ends up being 2 root 1 minus root 2 over, this just ends up being basically a difference of squares. So we're going to have 2 root 1 squared minus root 2 squared. So we still have 2 root 1 minus root 2. Now, 2 times root 1 squared, well, root 1 is just 1, so we're basically saying 2 squared, which is 4, minus root 2 squared is 2. So 4 minus 2 just ends up being 2. And that's all we have for this first term. Then we rinse and repeat with this next term. So I'm just going to go ahead and copy that. Then, let me just line that up real quick so that it's kind of, there we go. And we're going to multiply by the conjugate once again, which would be 3 root 2 minus 2 root 3 on the top and bottom. And I'm sorry if the square roots are a little squiggly. I'm kind of going through this a little bit fast. So we still got this term on top, and then we have another difference of squares on the bottom. And yes, if I'm working through this a little fast, it's because we should already know this. You should be very familiar with this already from telescoping part 1. So if you're not, I would recommend checking that video out. So 3 root 2 squared is just 3 squared times 2, which is 18. And then 2 root 3 squared is 4 times 3, which is 12. 18 take away 12, that's 6. Cool. I'm just going to do the terms that we can actually see. We multiply by its conjugate. That just ends up being, and I'm going to go through this a little bit quicker. So I'm sure you can do this slowly on your own at home, but it's basically 4 root 3 squared minus 3 root 4 squared. When you simplify that, that just ends up being 12. And let's do this last term that we can see. So this term at the end, I'm just going to put a little dot 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 because obviously everything else in the middle we can't forget about. And this ends up being, just trying to be a little bit more efficient. So I'm just literally going to take that and copy and paste it. I believe I've done it to the side. It says 9900. Cool. I'm going to add another page. So basically, what we're summing up now is from our original expression, we got something like this. So I'm going to take all our rationalized terms and we're going to see what we can do with them. Oh my gosh, that's crooked. Okay. So obviously this is taking up quite a lot of space, but just bear with me. I think because it's taking up so much space, we should shrink that down just a little bit, just so we can fit this. The thing is, everything in the middle is going to be summed up until this thing over here. Okay, and from here, we can do a bit more simplification because we can actually remember that we can split these fractions up because right now they do not have the same denominator, so we can't exactly combine these fractions. So instead what we're going to do is let's see what happens when we split them up. And by split them up, I mean something like this. So let's look at this one first. So this can be split up into 2 root 1 over 2 minus root 2 over 2 if you just split the fraction up. So 2 root 1 over 2 just ends up being root 1. And then we're going to take away root 2 over 2. And then we're going to split this fraction up as well. 3 root 2 over 6 minus 2 root 3 over 6. And we're going to keep going. So we're going to split this up. And it might not look like we're doing much right now, but just bear with me. It's all going to come together in the end. Yeah, and one of my biggest annoyances with this telescoping unit, I really like it. It's just, we just don't have enough space. So I always have to do this, which is kind of annoying. I would prefer it if everything was on one line, but it's okay. Okay, and now let's do some more simplifying. So always remember, in math you want to simplify as much as you can. Because what we have here is we have a factor of 3, which will go away with this 6. This 6 becomes a 2. And now I think you see what we have. That fraction simplifies to root 3 over 3. The 4 and the 12 will simplify to a 3 in the denominator. So 4 goes away, 12 becomes a 3. And we keep going. So I think you can see that we got what we're looking for. So you can see we got negative root 2 over 2 and a plus root 2 over 2. So we know that those will go away. And then we know that these two terms can go away as well. So let's just make that clear. This is our cancellation. So everything in the middle is going to go away. All the way until this final term. Sorry about that. I'm kind of on a weird angle here, so it might be a little squishy or squiggly at the ends. In the end, all we have are the first term and the last term. So we have what we want. 2 terms. All we need to do now is find out what 1 minus the square root of 100 over 100 is. The square root of 100 is 10. So we're basically doing 1 minus 10 over 100 10 over 100 is the same as 1 over 10. So in the end, we're doing 1 take away 1 over 10, which ends up being 9 over 10. So there we go. That was our warm-up problem, and that was basically telescoping in action, where we had to rationalize the denominator. So I hope that was pretty familiar with you. If not, again, as I said, go back and review telescoping part 1, because now we are going to get into some more fun stuff, some different techniques that was not covered in part 1. So let's take a look at our first problem today. So our first problem asks us to find the sum of k factorial times k, where we are summing the k's from 1 all the way up to 2023. So for each of the problems that we're going to do today, I have put this little box over here that says technique. And then what we're going to do is we're going to fill out the big important technique that we use to solve this problem. So I'm going to do that along the way. Okay, this way you have a few good ideas to keep in the back of your mind. Okay, because it's very important to not just solve it, but to understand the big fundamental techniques involved. Okay, so we know we need to get this to a telescoping form, only because, we're covering it today, but how would we do that? How are we going to get this thing to telescope? Because right now it's not really in that form. So you can see, if you remember part 1, this thing isn't really in a plus minus form yet. There are no fractions, so it's not like we can cancel anything from the top or bottom, and it's not like there's anything over a square root. So what is there to rationalize? So at first it might seem like, even if, let's say, even if we were to just write this out, right? Like 1 factorial times 1. So basically we're just writing out the sigma into its explicit form like this. And then we bump that up to 3 factorial times 3. So basically this is what the sum means. And then, at the end we got this huge 2023 factorial times 2023. And this doesn't really look like anything telescopes. Where's the cancellation? What is supposed to cancel with what? So at first we might seem stuck until we remember the power of adding 0. What do I mean by that? Well, in a telescoping series, what we need is, if we go back to what we're trying to do today, so all problems will use something like this. We want a minus sign to get involved, so let's get a minus sign involved, shall we? We need to remember that k equals k plus 1, take away 1. Because 1 minus 1 is 0, and then we're just left with k. Now, why would we think to write it like this? Well, this is going to help a lot. Because this is how we're going to get this minus sign involved. So, if I take this question that we have to evaluate, this time, this k over here is just going to be replaced with this, because they are equivalent. So if we just pop that in here, awesome. Like this. And actually, I'm going to put another pair of brackets just like this, because what we're going to do is now we are going to distribute this k factorial across these two terms, because we know k factorial times k plus 1. Do you know what that is? I think you do, because k factorial times k plus 1 is k plus 1 factorial. Now it's time to distribute this k factorial times -1, so still preserving the negative sign. But now we're going to take away k factorial. And now I think we have what we are looking for, because now if we are to write out this sum explicitly, and I'm going to start with the end over here, so this 2023, instead of starting from the bottom with this 1, but it's the same thing because again, the order in which you add and subtract doesn't really matter. So if we were to start with 2023, our first term would be 2023 plus 1 factorial minus 2023 factorial, so that's 2024 factorial. Take away 2023 factorial. The term just before 2023 was 2022. And when you pop 2020, like k equals 2022, you're going to get this. We are summing this up, and I think you can see already we got what we're looking for. This negative 2022 factorial will cancel with a positive 2022 factorial. And then we are going all the way down to, well, we started at k equals 1. So we have a 2 factorial minus 1 factorial. And we know the term before this looked like 3 factorial minus 2 factorial. So we know this can go away. And there we have it. So this is our final answer. It is just 2024 factorial minus, well, 1 factorial is 1. So we're just going to leave it like this. And that's good enough for me because 2024 factorial does not have to be written out. Okay, it's way too big. So that's good enough. So if we were to go back here and ask ourselves, what was the technique involved? I think I can pretty concisely summarize it as add 0. You're going to be seeing this a lot in math and higher level math in general, so better get used to it, okay? This was our first technique, add 0. That's what we did over here. That's the only way we got our terms to collapse. That sound good? Cool. Let's go on to question 2. Okay, so question 2 looks pretty scary, okay? Because we got another sigma from 1 to 99, but now this time we got some square roots in the denominator. You know, we got a square root of k over here, and then we got a square root of k plus 1, and then we're, you know, adding them, we're multiplying them by all of this. So what do we do? So the reason I selected this problem was because I want to make a point. So let's get straight into it. And what's the point I want to make? The point I want to make is that this problem is nothing special, basically. So I want you to use the same technique that you've always done, even for a scary looking problem. That's something you're going to have to get used to in math, okay? Even if it looks scary, don't forget your fundamentals. So what do I mean by that? Well, whenever you have a square root in the denominator, we really only have one thing that we can possibly do. And if you remember the warm-up problem, it's time to rationalize. So let's go ahead and do that. So basically, man, this is like my favorite function of this app. It's just, I love copy and pasting because I can just do this. All we have to do to rationalize is to take our term on the bottom and take that sign and flip it to a minus. That's all we can do. So let's rationalize this. That ends up being this term up top take away. Okay, now we have to work with the bottom. So on the bottom we have k plus 1 times root k squared. So all of this is squared, so I'm going to put another bracket. And then, just to stay organized, and then we're going to be taking away this term squared. So this ends up being let's see. We're going to square everything. So that's k plus 1 squared. Square root of k squared is just k. And then we're going to be taking away k squared times k plus 1. All right. Now, let's see if we can simplify this denominator a bit. So I'm going to pull out a common factor of k and times k plus 1, because what we're left with is we got one copy of k plus 1 still inside, and then we have a k still inside. So let's just mark it like that. But the great thing is that k over here is going to cancel with a minus k over here. So when we multiply by a positive 1, nothing changes. So basically what we're left with is all of this over k times k plus 1. And I'm sorry if I went a little bit quick there, but I think if you just look at this slowly, you'll see how exactly I got there. Okay? Right now, I'm sort of going through this a little bit quicker, only because I want to show the main fundamental technique in action. So not too concerned with all the intermediate algebra steps. Anyways, now, what we can do is, we're almost in the home stretch, guys. Stay with me. As we saw in, was it the previous problem? No, it was in the warm-up example. Yes, so in the warm-up example, that's where we split up the fractions once again. So I'm going to do the same thing here. We're going to take this, and I'm going to show it a bit more slowly this time. I'm going to take this fraction and split it up. Because now, guess what? We got even more cancellation. K plus 1 cancels with k plus 1. K cancels with k. In the end, we are left with root k over k minus root k plus 1 over k plus 1. Okay, and I'm going to need another page because I always underestimate just how much space we need. So basically, we can take this entire expression and now we can actually get rid of this thing and replace it with this, because that's what we've simplified it to. So now what we can do is we can write out this sigma sum explicitly. So take your k equals 1 and just plug it into here, and then work your way up to k equals 2, 3, 4, blah, blah, blah. So when k equals 1, we first have a term that looks like this. When I plug k equals 2, I get a term that looks like this. And this is going to continue until, let's see, when I plug in k equals 98, I'm going to get something like this. And then finally, our last number, 99. Remember, top number is where you stop at. That ends up being, I'm going to give myself a bit more space. That ends up being this last term here. So, if this looks familiar to you, and it should, in fact, it looks very, very similar because it's actually the exact same as the warm-up example, basically. Because we're going to get the same answer. Root 100 over 100 is 10 over 100. As I said before, that's 1 over 10. So we get a final answer of 9 over 10 once again. So, what was the big lesson to be learned from here? The big technique? I would summarize it as, do not be afraid to rationalize. Quote unquote, scary expressions, because as we'll see, it ends up collapsing just like an easy problem. So basically, this ended up being very similar to our warm-up example. And in fact, we got the exact same number. So I like that one. That was great. Yes, so that's the point. I don't want you to be intimidated by these complicated looking expressions. Just use the basic technique of rationalizing, and you'll be fine. So, how are things going so far for you? I hope you're enjoying the ride, because we got a lot more to go through with question 3. Something like this. So this time I did not write it in sigma notation. I just wrote it out explicitly like this. But in this solution, we are actually going to turn this into sigma notation because it should help us a bit. But I'm not going to say too much. I'm going to let you have a go at this first. Okay? So at first, we might not know what to do for something like this. So whenever you see a problem like this, I would say the first thing that I'd notice is that's not black. We notice that we're basically, all terms look sort of similar. They have the same form. It's basically 1 over 1 plus 2 plus 3, right? All the way until n. So whatever that n is. So whether that n is 4, 5, or 99, doesn't really matter. They all have this basic form. So they all look very similar to each other. And I think we can use this to our advantage. Okay? If all numbers have a similar, all terms have a similar form to each other, that's usually your sign to see what's going on a bit. Okay? And this is where I want to emphasize that you need to use everything you know in math. Okay? So I know I'm in the telescoping series unit right now, but I don't want you to just limit yourselves to like just telescoping. Okay? You need to pull out everything you know in math. And one thing that's jumping out is I hope this looks very familiar to you. I hope you are just screaming. That looks very familiar. Because yes, it does. whenever you see yourself having to add all numbers from 1 through n, we have a very useful formula for that. Basically, adding up all numbers from 1 through n can be represented. It's equivalent to this formula here, n times n plus 1 over 2. Thank you, Gauss, for that. But if you did not know that, don't worry. I have a video on that as well, going over that, and it's very important to know that. But with that being said, now that we have this, we're going to do some more simplifying. So basically, whenever you have 1 over now this fraction over here, we can basically flip the top and bottom. So basically, that is equivalent to this. Okay? And when I said that you need to use everything you know in math, I mean you need to use everything. So, as I said before, I was going to introduce sigma notation. I think now is the time, because what we can do now is we can represent every term like this. So, we're going to start from n equals 4 this time to n equals 99. And then we can put this as our formula inside the sigma. So I'm just going to move this down a bit. And the great thing about sigma is we can actually pull this 2 out. So that's on the outside, and then we can just concentrate on this term on the inside. And because we pulled a 2 out, sorry, I'm going to need a bit more space. So because we pulled a 2 out, what we're left with in the end is a 1 over here. Amazing. Going back to what I said earlier, when I said you need to use everything you know in math, if you recall from telescoping part 1, this is equivalent to 1 over n minus 1 over n plus 1. This was one of the handy identities that we used in telescoping series part 1, although I did not show how we derived it, because that's for a future video called partial fraction decomposition. It's just enough to know this for now, okay? So that certainly helps, because now this thing is the same as this. So we're going to replace it with this, just like so. Again, gonna need another page. But this over here should not be too bad. I don't know why I did that again, but I think it's because I just want to put this on a new page actually. So this should be easier for us because I'm going to keep the 2 on the outside for now. And on the inside, what we have is, starting with this time, n equals 4. Okay? So not n equals 1 or n equals 2. Be careful. N equals 4. Then we're going to go up to n equals 5. And this will continue until n equals 99. But just to make it clear, I'll write from n equals 98 going to be taking away 100, 1 over 100. Because now we can see my favorite part always of telescoping is just this satisfying cancellation. Everything goes away. And our final answer would be 1 over 4 minus 1 over 100. And if you said that, you would be wrong because the final answer is actually twice as large as this. So don't forget about your 2 that you stuck in the front at the very start. And I think the easiest way to do this would just be to distribute. So 2 times 1 over 4 is 1 over 2. And 2 times 1 over 100 is the same as 1 over 50. And when we simplify this, this ends up being 24 over 50, which is the same as 12 over 25. And there we go. So this sum ends up being 12 over 25. So what was the big idea over here? In this problem, we need to use everything we know in math. So you can't forget things and get stuck and say, oh, I don't know what to do. Wrong, you do know what to do. For example, over here, what did we have to use? Well, we had to use the fact that the sum of the first n positive integers is equal to this. Again, thank you, Gauss. By the way, for those who don't know, I am saying Gauss, G-A-U-S-S. He was a great guy, great mathematician. Anyways, what else did we have to use? Well, we can't forget about what we learned in part 1 over here. So it would be this fancy way to split up the fraction in a way that will actually get us to telescope successfully. Great. Moving on. Question 4. So this one is my personal favorite of all the questions that we'll be doing tonight because, well, I couldn't do it. So I like problems that I can't do, and I like sharing them with you guys. So if you can do this one without me before I actually, show you how to do it, then congratulations. You are smarter than me. You are better than me. You know how to telescope better than me. But if you can't, don't feel too bad because I couldn't do it either. Okay? So let's get into it. So somehow we have to show that this giant thing in the middle, so that's 1 over 2 times 3 over 4 times 5 over 6, so on and so forth until 99 over 100. We have to show that this is somehow bigger than 1 over 15, but smaller than 1 over 10. Okay, so this one seems a little challenging because as it stands right now, there's currently no telescoping going on. But we would like to introduce telescoping into this problem somehow. So we can imagine if it would be really nice if we could somehow bring in maybe a 2 over 3, a 4 over 5, a 6 over 7, because then we know that that product can telescope. Because the 2 would cancel with the 2 over here, the 3 would go with the 3, the 4 would go with the 4, 5 with the 5, so on and so forth. So maybe we have to do some work to introduce this telescoping product. So let's see how we can do that. So how about taking this thing in the middle, and from now on, let's go ahead and call this thing, let's go ahead and call it A. This way, this is a good strategy, because this way, now I don't have to always read out the product. I can just call this thing A for this solution. Now, because our problem is involving these strict inequalities over here, let's try and see if we can impose some conditions on A. So specifically, if we can show that A is less than something, that would be great, because that's what we're trying to get in the end. We want to show that A, so this thing, is less than something. And we're going to do this by analyzing each term in A individually. So what do I mean by that? Well, let's take a look at this first term over here, 1 over 2. Now, 1 over 2 happens to be less than 2 over 3. And I'm actually going to move this down so I can give myself more space. It's a little cramped right now. We go to work with the next term, 3 over 4. 3 over 4 happens to be less than 4 over 5. Five over 6, same logic, happens to be less than 6 over 7. Seven over 8 is less than 8 over 9. And in general, I'm going to do a little aside here. So in general, you take a fraction, A over B, and you add 1 to both the numerator and the denominator. You'll find that you get this inequality. And we're not going to show that in this video, because this is a topic, a very important topic for another day, but for now, you're just going to have to assume that this is true. Even though it's not necessarily too hard to show this, it's not something I want to go over in too much detail in this video. So for now, you're just going to have to trust me that this is true. So this means our last term, 99 over 100, is less than 100 over 101. So we see if this first term is less than this term is less than this term is less than this term, so on and so forth until this term is less than this term, then when we multiply all of these terms, it should be bigger than when you multiply all of these terms. So that's where we get this first inequality. So A is less than all of this on the right-hand side. Cool. Can we do something similar for A greater? Yes, we can. So for A greater, what I'm going to do is this time we're going to keep the first term the same. So we're not going to change this half, okay? But for this 3 over 4, now we can see that 2 over 3 is less than 3 over 4. And I think you see why I had to keep this half term the same. That's because 2 over 3 we've shown is less than 3 over 4. So we've taken the 3 over 4 and just subtracted 1 from the numerator and the denominator. But if we were to do that for this original term, well then we would get 0 over something which is just 0, which is not what we're trying to go for. We know 5 over 6 is greater than 4 over 5. We know that 7 over 8 is greater than 6 over 7. And this continues until this last term, 99 over 100, we know is greater than 98 over 99. So why did we do all of this work? Well, now we can see. Let's go ahead and number these actually. So I'm going to go ahead and call this important discovery number 1, and let's call this number 2. Now let's see what happens when we multiply 1. So let's multiply number 1 by A. So if we go ahead and do that, so let's take this. I'm going to show you what we're going to do. So right now this is equation number 1. What we're going to do is multiply by A on both sides. This left-hand side just becomes 2 copies of A, which is A squared. And if we recall what A was at the start, we said A was just this original expression. And now, if we just multiply A by what we found over here, we get this telescoping product. And since this is a telescoping product, this 2 will go with this 2, this 3 goes with this 3, and it continues. So in the end, we are left with A squared is less than 1 over 101. So that's good to know. We're going to do the same thing for equation number 2. So we're going to take equation number 2 this time, and we're going to multiply it by A. This time I'm going to have to copy equation number 2 over here. Same thing. I'm going to take this A and multiply it on both sides. This way, this time we get A squared is greater than, this time it's 1 over 2. We have 2 copies of this, remember. But now we have the rest of the product, which is telescoping. So, what goes away? Well, starting with this 2, this is the telescoping product. But this time, because we have this extra half term at the start, what we're left with is A squared ends up being greater than 1 over 2 times 1 over 100, which is 1 over 200. Okay, so I think we should highlight these findings and combine them into one long inequality chain. So we know that sitting in the middle, we have a squared. We know that it is less than 1 over 101, and we know that it is bigger than 1 over 200. Now the thing about 1 over 101 is that 1 over 101 is actually smaller than 1 over 100. And the great thing about 1 over 200 is it happens to be bigger than 1 over 225. So here's the thing. If a squared is less than 1 over 101, then a squared is definitely less than 1 over 100, because 1 over 100 is greater than 1 over 101. If a squared is bigger than 1 over 200, it is definitely bigger than 1 over 225, because 1 over 200 is already bigger than 1 over 225. And why did I pick these numbers? Well, that's because, if you remember, at the start, what did we want to show? We want to show that a was bigger than 1 over 15 and smaller than 1 over 10. And if you know anything about perfect squares, then you'll see what I've just done. And in fact, the solution is basically done. If I were to take the square root, these are all positive numbers, and let's ignore this and focus on the numbers at the end. In the end, we have shown, when we take the square root, we have shown exactly what we want to show at the start. So this problem is finished. There we go. I hope you enjoyed that one. As I said, this is probably my favorite problem that we do tonight. And I've given something similar in the homework. So you can have fun with that. Let's get to question number 5. All right, that just reminded me because I saw this technique box. It reminded me that I have to go back up here and write out the big idea. So over here, the main technique is to introduce a telescoping series through multiplication. Awesome. Now let's get on to question 5. Okay, this one is pretty scary as well. Oh my gosh. So we got we got a bunch of terms that go like 1 plus 1 over something squared plus 1 over another number squared, and then we got square roots involved, so it seems pretty hard. Until we take a step back and realize that, hey, you know what? Actually, all of these terms in the sum, they all sort of follow the same form, if you know what I mean. So basically, we're always going to be taking the square root, but inside the square root, the numbers sort of have the same structure. It's basically just 1 plus 1 over a number squared plus 1 over the number over here plus 1 squared. Right? We can see 2023 is 2022 plus 1. 2024 is 2023 plus 1. 3 is 2 plus 1. So they all sort of have that general form. So maybe, in fact, we can do something with that. So what we're going to do this time is we're going to sort of be a little bit more general with this thing. So for every positive integer n, let's analyze a number that looks like this and see if we can simplify it. So the reason we've chosen something like this is because that's what all the numbers over here look like. They all follow this structure. So sometimes it's best to work a little general and see if you can simplify this, for example, this sum. The easiest way to do that would probably be to just combine everything into one fraction. So if we put everything over a common denominator, it would be this. Just multiply those two together. And I'm going to be going through this a little bit quicker, but you can do this at home on your own as well. I trust you know how to combine fractions, but in the end you're going to get something a little bit like this. From here, what we can do is we can expand this top expression here and see if we get anything interesting. So let's open all of that up. And after combining everything, what we're going to get is something like this. The crazy thing about the numerator is it actually factors very nicely into something like this. And just if that was a little too fast to see how we went from here to here, we can just sort of tell for anything that goes a plus b plus c squared, where a is n squared, b is n, and c is 1, we can see we've produced an n squared squared. We get an n squared term, and then we have a 1. And then the remaining terms is going to be twice the product of each pair. So n squared times n times 2 will give us 2n cubed. N squared times 1 is n squared times 2. That's 2n squared plus the n squared term from before gives us 3n squared. And then n times 1 is n times 2. That gives 2n. So that's just a little something to think in your head. As you get more practice, you'll be able to recognize that quicker. Anyways, this is great because what this means is now every term looks a little something like this. I'm sorry, this is bugging me a little. It's just very not straight. There we go. And you already know that this square root undoes the square function. So it's almost like we just have this. And this is the same as this when we expand this n times n plus 1 out, because it allows us to, gonna add another page, sorry about that. It allows us to split the fraction up very usefully. So we can split it up as follows. Because this is just 1 plus 1 over, and I'm actually going to go back to the form that we were in before, so basically just the factored form, because I hope the alarm is going off that this looks very familiar, because this can actually be split up into the difference of the two fractions, which we learned about before. So again, we have to use everything that we know. Now if we go back to our original problem, I think now that we have a general formula, we can put this into sigma notation. So what we're going to be summing up is something like this, but now we need to set our boundaries. So first, we're going to be starting with, I believe, n equals 1. Yes. So we're going to be starting with n equals 1, and then we have to go up until n equals 2023. So now we can actually write this sum out explicitly. If we start with 1, we're going to have to be very careful that we stay organized. So let's just spell out the sum. It would be something like this. Cool. And then when n equals 2, we're going to get something like this. When n equals 3, we're going to get this term, and it keeps going. So let's keep track of what's going on. So this negative half is going to go away with this half. This negative 1 over 3 is going to go away with this 1 over 3. This negative 1 over 4 is going to go away with a 1 over 4 somewhere later, the next term down the line. And this sum will just keep continuing until n equals 2023 minus 1 over 2023 plus 1 is 2024. So there was a negative 2023 term that goes away with this 1 over 2023. So, and this negative 1 over 2024 doesn't cancel with anything, which means in the end what we have is we cannot forget about these 1s at the start of each term. So how many copies of these do we have? Well, we started with n equals 1 up to n equals 2023, so we have 2023 copies of these 1s, but we have this extra one term here which did not cancel with anything. So we have to include that in the final count as well. It's actually 2023 plus 1, which is 2024, but then we have to take away 1 over 2024 at the end, because that did not telescope. And this is our final answer. So, pretty cool problem if I do say so myself. So, what was the big technique in this problem? Well, if we look, we had to work with a general n, because we realized all numbers had, all the terms in the sum sort of had the same form, as I said before, this form right over here. So we worked with a very general n, and then we actually simplified it through some algebra to get a form that we know telescopes. We get this very familiar 1 over n times n plus 1, which we know we can split into two fractions, which is great. And then after that, we put everything into sigma notation, write everything out, spell out the sum, and then keep track of what cancels with what. So, lots going on, lots going on. So here, the technique is to try your best to find a formula for the general terms. So you're going to be describing everything pretty generally in terms of n instead of a specific number. And you should do this especially if all your terms in the sum have the same form. So what do I mean by that? I mean that every term in the sum looked identical to each other. Okay? So they all have a square root. They all have a 1 plus 1 over something squared plus 1 over the number plus 1 squared. So 1 higher. Great. That is amazing. And now, maybe we can do something similar for question 6. So this time, question 6 says, let an be a sequence of numbers with the property that when you add up a1 plus a2 plus everything up to an, you get this closed form formula. For all n greater than or equal to 1, evaluate 1 over a1 plus 1 over a2 plus all the way to plus 1 over a 2024. Yes, that is the year that we are doing this problem. So, hopefully we can get something to telescope. That would be very nice. Now this time, what we're going to do, the best way to do that would be, I'm going to take this formula and paste it over here. Let's go to a new page. Now this time, I think what we're going to do is my goal would be to find an explicit formula for an by itself. So not including a1 plus a2 plus everything up until an minus 1. I'm ignoring all of those terms. I want to find a closed form formula just for an. And I'm thinking to do that because in the end, we have to sum up 1 over an individual term. So we're not asked to sum up 1 over a1 plus a2 plus a3. That's not what we're asked. We're asked to do 1 over a1 plus 1 over a2 plus 1 over a3. And there's a big difference between the two. So I think it would be a good idea to find a general formula. Now the best way to do that for a lot of these closed form problems would be to just plug in the formula but stop just 1 shy. This means because this closed form formula over here holds for all n, so it would hold for 1, n equals 1, n equals 2, 3, 4, 5, it will hold for n minus 1. This means all we have to do is just plug n minus 1. So n minus 1 is basically like our new n. Okay, that means wherever we see an n, all we have to do is just replace it with n minus 1. And I'm actually going to write it out slowly in case this concept is foreign to you. So make sure you see how this works. This n minus 1 is basically going wherever we see an n. Okay? We can clean this up a little. This ends up being n minus 1 times n plus 1 over 6. And now, this is a very common strategy in sequences and series. We can get the general term an on its own, because all we have to do is take these two equations that were given here and subtract them from each other, because a1 is going to go with a1, a2 is going to go with a2, everything up until an minus 1 is going to go away, and then we're left with this an term. So let's do that. Save us some time. We're just going to paste these. Because these two fractions have the same denominator, we can combine them and start to clean up. So I think the easiest way to do that would be to actually factor out this term n times n plus 1, because it's common to both of them. Then what we are left with is an n plus 2 term minus, and we have to be careful about our minus signs, minus n minus 1. Okay, so this n term would cancel with this minus n. Minus 1 becomes a plus 1 plus 2, that's plus 3. So what we really got is something like this. And the great thing about this is that this can be reduced to n times n plus 1 over 2. Now, because in our sum we are asked to evaluate 1 over a1 plus 1 over a2, you get the idea. I think it would be a better idea, now that we know what an looks like in general, then we can say that 1 over an ends up being, we found a very general form for an. It was this over here. And 1 over this ends up being just flipping the fraction, something like this. Sorry, I'm very picky. There we go. And the great thing about this is now we can put this into sigma notation. Because what we have to do is, now this is the general an, 1 over an. And let's see. We have to start from n equals 1 up until 2024. Now the great thing is we can pull out this 2 from our sigma, and we are left with 1 over n times n plus 1. So again, we already know this because we know that this 1 over n times n plus 1 can be split up. Yes. We know it can be split up into 2 fractions. The difference of the 2 So I think for these problems, I definitely need a lot more space. I didn't realize my writing would be this big and we would be taking up this much space. Maybe because the sigma is just so big. Might have to reduce that down. Anyways. So we still got 2 here, but now I think it's time we write out this sum explicitly. So, starting with n equals 1, the first term will look like this. When we get to n equals 2, it's going to look something like this. And I think you see where this is going. This keeps going until n equals 2023 will look something like this. And then n equals 2024. And I know this is really bugging some people, how it just like cuts off here, but oh well, that's the thing about telescoping, it's pretty long, but now we got this satisfying. Oh, it's very satisfying. Yes. And this final answer ends up being 4,048 over 2025. So if we go back and look at our work, what did we do? Well, I would say this first step was very important, finding a general formula for an. So that's what we did. This technique was to try and find a formula for the general term, so just like the previous problem, but this time we did it by subtracting. Two consecutive expressions. And I say consecutive because it's one after the other. So here we have the formula for the first n terms, and then we cut the formula short by just evaluating the first n minus 1 terms. So then when we took the difference, everything from a1 through an minus 1 would cancel, and then in the end we're just left with an an term. Excellent. And then from there, we were able to telescope pretty easily. Moving on to question 7. So something involving logarithms. Okay, so this time we are asked to find the sum of this complicated expression when we sum from n equals 2 to 127. So it seems like we've got some complicated logarithms involved. But we can see we have one with a base of 2 and another with a base of n plus 1 and another with a base of n. But we do see the number 2 over here as the argument and over here as well. This makes us think that we should convert everything to the same base, and I'm personally thinking base 2 because it's just easier to work with numbers than letters in general, but also that way we will get everything in terms of base 2. So that's what we're going to do. We're going to convert all our logarithms to base 2. Because if we have logs with the same base, then we can use our logarithmic properties to simplify things. So let's convert everything to log base 2. You may recall a little something from logarithms, this very useful identity that we're going to have to use. So if we have log AB, this is equivalent to 1 over log BA. So that's what we're going to use here, because log N2 is equal to 1 over log 2n. And then we also have log n plus 1, 2 is equal to 1 over log 2 n plus 1. So that means we can rewrite our problem as follows. So let's just copy this over, and this time we are going to replace everything with what we found from before. So these two expressions are going to go away. This last term still stays, and instead we're going to replace everything with what we got before. There we go. Now I'm not going to write out the sigma sign every single time. Instead, I just want to focus on the expressions involving log. So now what we can do is the term at the farthest right side, we can combine all the fractions like so. And then on the bottom is going to be these two. Just going to move everything around a bit. So let me give myself some more space. And now we can use our basic logarithmic properties. If you're not familiar with this, I would recommend checking out a video on log first. So this is another prerequisite. I'm assuming you already know all of these identities because I'm not going to be going over them in this video. And now we can split these fractions up. This means we can rewrite everything like this. So this is the sum that we need to evaluate. So I think it would be a good idea now to write out this sum explicitly. So we are going to start with n equals 2. Which would give this term here. And then we're going to increase. And then we're going to increase. to n equals 3. Which would give this term, and I think you can already see we have some cancellation going on, some nice telescoping. So this will continue all the way until let's do the second last term, would look something like this. And these would all go away. So everything in the middle goes, and we're just left with the first and last terms, which can be simplified as follows. So log base 2 of 2 is just equal to 1. So 1 over 1 is 1. And then we're going to take away, since 128 is equal to 2 to the power of 7, this means we are subtracting 1 over 7. So we get a final answer of 6 over 7. There we go. So the big lesson here was to convert everything to the same base. So that's a nice problem. So we have to use all our knowledge from other areas in math. So this one involved logarithms. Cool. Moving on to the final question of this video. So we have to sum up this pretty crazy expression. So we've seen crazy expressions before, but this one looks very, very nightmarish. And then we have to sum from n equals 0 all the way to this odd number, 287. So, as usual, I'm not going to start off with the sigma term. We're just going to start off with this thing inside. Let's see if we can simplify this a bit, because right now it's not very useful. It looks way too complicated. So what we can do first is let's try and factor, because we can see that we can pull out an n, and we can also pull out an n from over here as well. So maybe that will lead to somewhere nice. Factoring is always a good first step, especially when you notice that things can be factored. Because then maybe we could get some cool cancellation going. So let's do this slowly. So that's the same as if we factor, it would become n times n plus 1. And this factors as n times n plus 2. And we might be able to see right now that we could be heading on the right track, because we have an n plus 1 term here, and over here we have an n plus 2 term here and an n plus 2 term over here. So maybe we could be heading on the right path. Let's keep going. So that inspires us to continue This term factors as, once again, n plus 1 times n plus 3. And this last term can actually be factored as n plus 2. Again, n plus 2, we see it again, n times n plus 3. Okay. So I'm just going to be a little bit lazy here. Let's just pull this over. And now, we can split this term over here as the product of two square roots. So again, splitting this square root up. And let's do the same for all of these terms. Now we can pull out the square root of n from the first two terms, and what we're left with is, on the inside, square root of n plus 1 plus the square root of n plus 2. Let's also pull out, from the last two terms, we see a common factor of root n plus 3. And I'm just going to copy and paste. Okay, that's a little big. Okay, that's annoying. Maybe not. I'm just going to write it out. And now we see some cancellation can happen. We see every term has a common factor of this giant sum, root n plus 1 plus root n plus 2. So those can go away. So what are we left with? Well, on the top, we are left with 6, so just the number 6. And then on bottom, we are left with, I don't think I need that much space actually. I got fooled by the giant sum from above. But anyways, what we're left with is square root of n plus the square root of n plus 3. Awesome. So basically, we have simplified that giant mess at the start into this, which looks a lot neater. So our question is basically asking us to sum from n equals 0 to n equals 287 of this new, well, not really new, but this new looking expression. Time to add another page, and let's get to work for something like this. So I'm actually going to move this once again down here. So we have a fresh new page, and let's get to work. So we are in familiar territory now. What we have to do, because we have square roots at the denominator, let's rationalize. So that would be multiplying by the conjugate, which would be the square root of n minus the square root of n plus 3. So remember, this minus sign is between the two expressions. So we're not changing this plus 3 into a minus 3. No, that's not how you rationalize. This is how you rationalize. You are changing this sum over here. Okay, cool. So if we were to do that, this expression becomes 6 times the square root of n minus the square root of n plus 3. And then on bottom, we have a difference of squares that goes something like n minus n plus 3. So our n's will cancel. N goes away with a negative n. And in the end, this 6, we have a 6, and then we have a minus 3 on bottom. 6 divided by minus 3 is the same as negative 2. So in the end, we get something like this. That has to be summed from n equals 0 to n equals 287. Whoops. Apparently I copied all of that. So this is what our problem has become. Now we have to write out this sigma notation explicitly. So if we plug n equals 0, our first term will look something like this. Square root of 0 plus 3 is square root of 3. And then we have n equals 1. Let's bump this up. And then n equals 2. So this can keep going. Until n equals 284 minus root 287, and then root 285 minus root 288 minus root 286 and 289. And then finally, when n equals 287, we have minus root 290. And again, I need more page. I keep underestimating how much space telescoping takes. Now we can pull out a common factor of negative 2 and see what we have left. So we start off with square root of 3. Oh my god, see, this is what happens when I don't have this straight function. I just get like really wiggly lines. Okay, let's see what else we have left. So we have square root of 1 minus square root of 4. And then we have square root of 2 minus square root of 5. The term after, even though I didn't write it out, would look something like this. And you know what? Let's keep writing some just to really see the cancellation. So this is going to continue until all our terms at the end that we've written out. So now the question just becomes keeping track of what stays and what goes away. My god, see what I mean? It's like so shaky. And don't forget, we have this minus 2 up front at the end. Now, let's focus on what we have in the brackets. So, let's see, this negative root 3 cancels with this root 3 over here. Negative root 4 goes away with root 4. Negative root 5 would go away with a plus root 5 somewhere later. Down there, you can't see it, but it is there. Negative root 7 would go away with a root 7 later on. So all of these go away. And then minus root 287 goes with root 287. And there we go. It looks like that's all we have left. So in the end, we were left with 3 terms at the start, and then 3 terms at the end. But notice that the number 3 also appears here. So we're doing square root of n minus the square root of n plus 3. And in the end, what we are left with was the 3 beginning terms and the 3 end terms. So is this just a coincidence, or is this how it's always going to work out? I'm going to leave that as a thought just for you to think about. But anyways, now all we have to do is just some simplifying. So let's write out everything as simplified as possible. Because, let's see, this is 144 times 2, so we can pull out a 12 and leave a root 2. I believe this is 17, and this does not simplify to anything. Do some cleanup. I don't think I'm going to have to count this 0 anymore, because it's just 0. And then square root of 1 is just 1. 1 take away 17 is minus 16. Minus 12 root 2 plus, you can imagine there's a coefficient of 1 here. So that would be minus 11 root 2. And then we have minus the square root of 290. And I think we are ready to multiply everything by negative 2 to get our final answer of 32 plus 22 times the square root of 2 plus 2 times the square root of 290. And what a final answer that is. And I think that is a good place to end the video here with this pretty crazy expression, this pretty crazy final answer. So, what was the big idea here? Well, definitely, as seen from the start, the main technique or idea is factoring is your friend. So you can always rely on some good old factoring to do great things. So a little factoring goes a long way. Great. And now it's time for some homework. So now let's talk about your homework. Okay, so you have 3 questions. And I'd say if you understood everything we did today, this homework should be no match for you, but I will say, except for number 2, where you're going to have to get a little bit creative. So, just some little hints before we go. And I let you solve these on your own. For question 1, I would say, because obviously there's only 3 questions in the homework and we did 8 techniques in the video. So not all of these homework questions will be using all 8 techniques that we learned, but still, they're pretty similar. Now for question 1, as I was saying before, I would say to focus on the general term over here at the end and rationalize. So that's my hint to you. Just rationalize and see what you get. See if you can simplify this term into something a little easier. Because as it stands right now, there's no telescoping going on currently. So just ignore all of these numbers for now. I want you to just focus on this one, okay? And then for number 2, I would say this one is very similar to question 4 that we did in the document. So if you don't remember that one was the one involving the inequality. So it was this one over here. So yeah, I would take a good look at this one and then go back to question 2 because it's very similar. And then for question 3, even though I would say we didn't do something exactly like this, but you're going to have to do some clever manipulation. Mainly, notice the fact that 8 is equal to 3 squared minus 1. So that's how you're going to get a 3 involved, because as we can see right now, we got a lot of 3's. So we got to introduce a 3 somehow, because this 8 is standing out for just being very, very awkward. So yes, that's my big hint. 8 equals 9 minus 1, which is the same as 3 squared minus 1. And this time you're summing from n equals 1 to n equals infinity, but don't be too intimidated by this infinity. I think as you work through this problem, you'll see that it's actually very nice that it's infinity. So with that out of the way, this has been telescoping slightly advanced. So telescoping part 2. So I hope you enjoyed this video. I hope you enjoyed the 8 questions I picked out today. I had a lot of fun searching for them and solving them and sharing them with you guys, preparing the documents. So I hope you enjoyed and have fun with these 3 homework problems that I have left for you. And there's so many more telescoping problems, but I think the ones that I've chosen, if you really understand what I chose to show you, I think you should be prepared for any telescoping problem that comes your way. So yeah, I'm going to stop rambling and I'm going to leave you to solve these 3 problems. Have fun. Goodbye.